Well. Welcome, guys. Here we are in the day 4th of this challenge of 100 days of LeetCode. So today we're gonna start with the previous exercise that we left yesterday. That was this one, top K frequent elements. Yesterday we struggled a little because we were taking an approach that wasn't the most optimal. So that approach leave us this solution that is sincerely a trash solution because it takes almost more than 1 second when this should take, I don't know, probably max of 20 milliseconds. So today we're gonna take a different approach. So the that one is we are going to investigate how we can make this algorithm efficient. And with that in mind, I found this page, which is a really cool page because this tells us which algorithm should we use depending on the problem that we are tackling. So in this case, I think that I found this, and this is the kind of problem that we are facing currently. So is kth smallest or largest? And in fact, this is the exercise that we are doing. So this roadmap, or I don't know, mind map, dialog flow, tells us that this is the way to do it efficiently. So we researching about what these heaps are, because I don't have a clue of what it is this. So we will be in this day learning about this. I think it's important because if this dialog says that we should use this to be efficient, so I think that is the way. So let's read. Let's see what we found here. So priority queue and heap. This is what we are looking for. It's like a queue with hierarchy. I don't know if, but it's something like that because if you remember yesterday, let me check. This was the solution. So we created a hash map with the frequency of all the nums, but I think that the slowest part of this algorithm is the sorting part. So what I'm reading here is like, let me see. On the min max heap or sorting. This one, which was that we used yesterday, and we sorted the hash map depending on the value, right? So this line is what mess our our algorithm, because I think that is the slowest line in the code. So solution is here, and it's using a priority queue and heap. But what the fuck's that? I don't know. By the way, yesterday, well, in day 2 and 3, I had a couple of issues with copyright. So today I won't be listening any sound or any music in the background because I'm a little scared about getting on a strike or something. So this stream will be a little muted, or I don't know. Let me find some music without copyright. Music to to make the stream more enjoyable. I don't know. Epidemic Sound, I heard of this page, but and in fact, I really have been here, but I didn't create my account. So let me bring this. I'm gonna create my account and I'm gonna pick some song, some background music to harmonize this string. Let me find someone like classic to get in the flow state. Classic jazz. Are you sure that this thing does not have copyright or something? Let me check. Epidemic. Copyright. I'm not sure about this epidemic sound, so I will leave it there. So today's stream will be a little silent. So, well, let's get back to this concept. So, I'm gonna read a little bit. What is the relationship between priority queue? Priority queue is abstract data type, and heap is concrete data structure that we use to implement a priority queue. Insert. This is what we are needing right now. It's like a data structure that has some priority based on the key. Is what I'm getting of this text. I don't know. Patience. Just an example. Yes. Severity. Merge key sort list. Smallest element. Smallest element. This is our problem. So let me check this. The priority queue is in an array. To do this, we could try using unsorted array. One, so we have to put it at the end. Find the value. Yes. Yes, that's we are struggling. The open. There must be a better way, I think. Heap enters. Okay. It's on a special tree based data structure. Okay. I thought that it was like a list, but seems to be like a tree. I didn't use tree yet. Binary heap? What? Binary tree. This is interesting. Word. It is a valid heap. What? What? Particular carry heap. Key heap is a tree where the nodes have key children, okay? As long as the nodes follow the two head properties, it is a valid heap. What the fuck are heap properties? Well, there's there are two types of heaps: min heap, mat heap. Min heap is a tree that has two properties: almost complete. Every level is filled. Tap possibility. What? I think that we should move to the tablet to get these things a little, I don't know, a little better. So what it's saying here, every level is feels a possibility the last deepest level. Okay. For any node, its key. Okay. Its key priority is greater than its parent's key. Okay. So what we need in this, a max or a min heap? The key is less than its parent's key. It's a heap game bang heaps. Okay. The thing is that I don't get how we can use this heap to solve this problem. Heap's like a tree, okay? But we need to well, 1, 2, 3 heap, not a heap. Okay. Children less than parent. Children less than parent. Children less than what? Oh, okay. It's always following the hierarchy level. So a children must be greater than the parent in this type of heap, because this has this flow and this one has, let me zoom this a little bit because it's a little small. Note that number in each node is the key. Okay, so these are the keys, not value. Okay, a tree node has a value. That's good to know. Keys are used to store nodes, construct trees. Keys are store nodes, construct. Okay. Values are the data that we want heap to store. But what is heap to store? Let me jump to translate. It's interesting. What? Heap to store. Heap to store. I don't get it. This. Okay. Values of the heap, but I don't get it where the values are stored in this heap structure. So I just see the keys here. Well, we'll find out. Like binary search tree, there is no comparable relationships between children. Okay. A third example here. There's no comparable. Okay, what is this saying here is that in this row, this level of the heap have 17 and 8, so these are not arranged like in ascent. They are not sorted left, right. Okay. In fact, there's no comparable or okay, these ones, any node, I don't know if it's well called, any node is independently of its siblings, brothers, I don't know. Okay, I get a little bit. Why heaps are useful? At first glance, heap is not data structure. Yes, it is. It is required to be a complete tree, but unlike binary search tree, it's not sorted. Okay, it's not sorted. This one is what it's saying, that all levels are not sorted. So this tree could be here, and this 2 could be here. Okay. Yes, that's the gist of this article. Why is this fucking thing useful? Okay. The heat of the heap is guaranteed to be all log n. Okay. So it's what? These bound operations that go to from root to leaf. Okay. Will be all log n. Okay. Because only nodes in a root to leaf path are sorted. Okay. But this paragraph or chunk of the text is saying, let me finish. What is this saying? Let me move this over there. Data is continuous. Okay. I'm getting this part. Completely understand this part. Because only nodes in a root to leaf path. Okay, root to leaf is like this path. It's like this. Are sorted. Okay, yeah. That is what this is saying. These lines must be sorted, like the columns of this grid-like structure, but the rows can be unsorted. Okay, why is that useful? Being complete also makes a good or right choice to store here. I don't know. I'll see. When we add or remove a node, okay. Okay, that's a good thing, I guess. If we need to add or remove a node is like this, like 2, like 1, like 8. This is a node. And if we have to remove that, we only have to worry about the root to leaf path, or this way, not the level of the heap or the tree. Okay, so we will see operations. Insert a key into a heap, place the new key the first free leaf. Okay, property your choice violated, perform a bubble up. What the fuck? Swap? What is swap? Python? This even exists. No. Okay. 3 squared than 10. Ah. I'm getting. So if we insert a new node and this node is greater, sorry, and this node is less than its parent, we have to swap it, and so on and so on. So at the end we'll have like this root to leaf path sorted vertically, right? Okay, yes, this is what it's saying. This is what I just saying to you. We're done. Heap order is restored. Okay. Okay. Interesting. It's the name algorithm. Bubble ups. Swapping with this parent with until the order is correct. Okay. Yes. Not parentheses. Not parent is greater than not key. Okay. Swap. Yes. That's not as hard as initially seems. Okay, since the health of leaf is complexity bubble up is okay. Yeah, this must be current with the height of heap complexity, but complexity of what? Time or space? Well, I don't know. So they mean do they know with Minky and return? What? Okay, Leno with Minky and return it. Okay, I see. Yes. Minky and return it. Okay. So we can only delete like the last leaf of the tree because it's the less valued key, I guess. No, I'm wrong. Delete mean it deletes the first key. Okay. To do that, remember return the root since the node with the minimum key is not always okay. No? No. No, that's true because this is true since the node with the minimum key is always at the what? It's always at the root. Should be replace the root with the last node. The rightmost node at the bottom. Okay. It's like moving up all the nodes when we do this delete mean. If property 2 is violated, okay, perform a bubble down. Bubble down is like bubble up but inverse, I guess. Yes. Bubble down is moving this one to the bottom. Yes. 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 What this says we keep swapping between the current node and the smallest child until we get to the leaf. Okay, hence the bubble down. Same as bubble up. Yeah, I see that. Well, that's the interesting part. How to implement this shit. Complete tree makes no space waste. Since it can be stored compactly. Pointers are not needed. Well, that's a good thing because we are not involving with that yet. Okay. No. What? Okay. I see. I see what you mean. Okay, it's like left, right. Yes. It's like this flow. Trin, 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 trin. With a single array, we can do that. That's interesting. How we can know how many levels are of the tree, or how many leaves, or how many, I don't know. It's interesting. For node of index I Okay, I see what you mean. So this structure is like a fractal. We have this one, we have this one. So how could be the fourth level of this tree? This is interesting. Then we should learn our okay. Okay, we see this. This is a heap. Shit, this is a heap. The heap algorithm of Python. A heap. It's a complete tree, okay? Each node is a mean heap. Each node of a mean heap is less than all of its children. Less than all of its children. Less than all of its children. We'll synthesize this later. Remove element with priority is implemented with arrays. This is good. Don't need any weird data structure to do this, so it's good. Python comes, okay. Heap, okay. Element at top is smallest, okay, but we need a reverse heap. But we can do it with a main heap also. It will just need to reverse the result array. I got it, I guess. Okay, we can do it. Heap push takes 2 arguments, okay. The first is the heap, okay. I want to push the element. What? The second can be anything as it can be used for comparison, okay. Typically, we push a tuple since Python tuples are compares position by position, okay. Yes. Smarter than this is interesting. This is really interesting. Our little things of Python. We are discovering some Easter eggs of Python. Because the reason is smaller than, okay. 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 That is interesting. It's very interesting. Heap up, take a single argument heap, okay. Right, to the smallest element in the heap. Yes? Okay. Oh, we can push a tuple. This is good. This is good because here we need to push the number. Yeah, the number and the count. This is really good. This perfectly fits on what we are looking for. It's rather. So the goal of today is to improve our yesterday's algorithm, which was this one, which is really a trash in terms of time, because memory is good, but time is crap. So okay, heap with push, he push. Okay, this automatically handles the sorting. This is interesting. Heap up. So first element of the tuple will be the key. So this will be sorted. This is really cool. This is really good. Heapify? Heapify? What the fuck is Heapify? is this thing? Let me try this here. Description. Okay. Okay. Print array. Print. Let me see what this function does. We're just experimenting with heaps. Okay. None. 1, 3, 2. Okay. 1, 3, 2. Okay. Okay. So this sorts the list automatically without using sort. How is that useful? I think that I'm getting there. With a heap, this is really interesting. So with a mean heap, no. We just need until here. Let me check if I understand the problem right. So with a heap, I'm gonna try to do it, and then I will try to calculate. But this is really good. Yes. Okay. Heap. Okay. So it's gonna be good for item in nums. I'm gonna simply add it to the heap with the key value. Key is a num and value is the count. No, count. No, I get it. Look, this will gonna be the structure. I'm gonna add like this. Wait, the first element is the count because we need to sort it like, get it, the count and the number itself. So, but we don't need to sort all the, yes, you can do it like in a set. Okay, so what this thing, okay, we need to push to the heap with the nums that count item and item. It should be here the num instead of item, because num is a little clearer, I guess. Well, I'm gonna print a heap to see how it looks like. I'm gonna erase all of this because this is not efficient code that we are looking for. Efficient code. So what we have here. Count and none. What is the test case? No. What? Count should be what? 1, 3. What? But if I get it right, the first element will be the key. I don't know why the fuck is being differently. This is really weird. He push the same algorithm. Nums count. count. 1 times 3, 3 times 1, 2 times 2. But wait, this is not sorted. This should be sorted, right? It should be sorted, I guess. It's not sorted. Let me see this. Let me see this. So so here I should get 1 3. Why 1 3? What the fuck 1 3? 1 3 1 3. No, it's normal. What if I do this? And I reverse this order because it's being strange. I'm getting right. It should be sorted, right? Or I'm wrong. Probably I'm wrong. 1 3 2 2 3 1. So it's working good. This looks like it's working, but I don't find why. Am I wrong? Because I think that this is the key that sorts the heap, right? Max heap is to reverse the sign of the number before we push it into a heap and reverse it again when we pop it out. Okay. No, this is so weird. This is so weird. What if you use Shopify? What if we create? What if we do this? Let me try something. Count array will be like this. So instead of doing this, I'm going to do this. I'm going to count array that append nouns that count none and none. So here I should have this. No, sorry. I have to print this one. And what the fuck is? Ah, yeah. See what you mean. Need to add tuple here instead of 2 arguments. Okay. Okay. 3 1 2 2 1 3. Yes. 3 1 3 1. Yeah, 3 1. So this is sorted because here, yes. This case. Want to add another test case. Yes. Okay. Okay, if we have this one, then I can create the heap push using another for, I guess. No. Or yes, for item in count array, you want to add heap push h item. Yes. So let me see if this fixes the order. the sorts heap. Okay. 3 1 3 2 1 3 2. The thing is, the first level is 3, right? Yes, I see what you mean. So if we are doing like a tree, but we have to remember that the level, like the second row of this tree, is it's not sorted. So it can be at any order. So how we can sort that? Let me think. So the first approach is working. This approach is working. We don't need this. We don't need this, no. We just need to heap push here, but like here. How we do this? Yes, this should work. Now the second thing that we have to deal with is how we can count and not. Yeah, yes, count and not. Yes, yes, not. I don't know how this thing works. If you see, in this level it's not sorted, but the first should be the first. I don't know why. In this case, one is not. It's not being like the most frequent element. I don't know why. I don't know why. I don't know why. Think. This is completely new to me, by the way. Heap. I've never dealt with this in my current experience or making stuff with software development. But it's very, I don't know how to call it. It's like so specific. Yeah, it is so specific. Element at top is smallest. Is the smallest. Is the smallest. Shit, I forgot it completely. This should be the smallest one. So messed up. Yeah, I forgot that we are dealing with mean he, not max he. So we have to reverse the order somehow. How? This is just for the record. Providing forget this. Okay. So how we deal with that? If we have like a tree, the smallest element in the heap. Heap up can be useful. Yes, we can sort this. I don't know how these things will work, but okay, sorted h, this shitty variable name, but we'll deal with that. For now, in h, we need to s that h that append the heap pq heap pq that heap pop h, yes, heap pop h. So with that way we should have the sorted array from the lower to the most frequent, I guess. So I'm gonna leave this print over here. I'll leave this print over here, but I'm gonna print also this. So to think how this works. 1 3 2 2, yes. Not in H. Why the fuck is this? The light is not hip hop? What the fuck is going on? No, I think that we should range. Range and H. Yes. Yes. 1 2 3. Yes. Yes. But now we have to reverse. I don't know if this is performant. The reversing reversing the array. Let me see. Simplest ways to implement a max heap is to reverse the sign of the number before we push it into the heap and reverse it again when we pop it out. Okay, so I don't know. We push -1 plus 10. What the fuck does this? -1. What? 30 20. Ah, this is interesting. So we can do a bit complex. What? Time complexity? Exact derivation. We should do this? No. Let me see how this works. But hey, we're learning about heaps and we didn't know that before, so it's a great advance proof. In this way, append, but append is faster than insert, right? Append versus insert Python. Okay, yes, we need to append and reverse array Python time complexity. This is good. ON time. Interesting. Interesting. Oh, this is not the most efficient way to do it, like using reverse. So how can we reverse this? So we should use this. But the thing is, yes, no. Band, hip hop. That way we have this. This is interesting. For any range length age, yes. We are inserting in order. Yes. So we have this already sorted. So we have to reverse it. Why if I do this reverse? This can work? I'm not sure. Should work. None. Uh-huh. Can I see the runtime? Yes. So we are there, right? So now we should need to have this key, I guess. Yes. So I have to cut this from 0 to k. I don't know if this is performing, but anyways. Now I'm gonna return. Now this comprehension again. For element in what? This comprehension Python. Let me check this. This is good, but hey, we can do it cleaner, I guess, without using list comprehension. So let me check. It's easy. So we should let result. I'm gonna have this, create an empty array, and for I in range k. This is good. Yeah, I guess. Result that append sh position I and the value of 1. Yes. Print result. I guess it's done. If I'm not wrong, it should be done. 1, 2. Yes. Case 2. Case 3. 2, 1. Yes. And it's what it is, brothers. I think it's done. Turn result. Yes, I think it's completely done. Let me comment this one, and voila. Yes, runtime 0 milliseconds. Holy shit, this is huge. Well, moment of truth. We'll see if this improved or is even worse than before. Let me check what the fuck I'm doing here. Let me change. So we are using a heap, then we are getting sorted heap, we are reversing it, and then we are just adding to the array the result. So it should be done. We don't even need this reverse. We can iterate the array from the end to the beginning, I guess. Yeah. Yes, but let's submit this and then we will make some touches to that. It's even worse than before. Shit. No, it's a real trash. I don't know if it's because this this reverse method, I guess. Yes. Yes. So we are not going to reverse anything. We will need just to hmm, range. We change range Python the docs to range decreasing Python. 10 to, yeah, what I need. 10 to 0, and the third argument is just -1. Yep. So, yes, it should be done, right? Mm. No. Length of message, uh, length of, yes, minus k, yes. Print result. Index out of range. -1. Final index will be length of -1. Yeah. Final index minus k. Yes. This can be better because I'm not using reverse anymore. So only thing, try it. If this don't work, I don't know what else to do. No, it's still a trash. I don't know, guys. But hey, we improved memory. But runtime is so bad. I don't know why it's so bad. Range is very sad. What if we don't use set here? This can improve anything? Stop it. Judging. It's judging. What? Ah. fact that this, no, I don't know what else to do. We researched about heap, but this doesn't look like it's improving. Should we get this? Should we see the solution? What do you think? Let me think. Because we are currently like an hour of a stream, and I think that we have to move on. So the next, yes, I'm gonna see the solution of this. Because you're witness that I've tried a lot of things and I just can't. Submissions. Submission is it's really bad. In fact, it was better the first solution with this comprehension than this one using heaps. So no. Let me see what this algo monster. Okay, Legos and top K frequent elements. Yes, you're given an integers. Your task is find. Your problem is to identify which elements appear the most often in the array. Remember two top key elements. Yes, 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 yes. Intuition. Yes, 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 yes. Yes, hash table or dictionary. Perfect. Count is count function Python performance. Seems like count function is trash. We should just add a hash table. Okay. It's okay, which has a consideration. Okay, yes, this is what we have done. Inefficient, yes. Just need K of them. Priority queue, yes. Yes. Clever. Size key. This can be the size. Can be the size of the heap because we are making the heap of n regarding size. Yeah, the elements whenever the heap 6 side we remove it. Holy shit, this is interesting. Hmm. Okay. Well, that is shooting, but if approach is efficient with case much smaller than the number of unique elements. Okay. How the fuck we can make a heap of size k? First count the frequency, then select the top key. Top key. Yes. Okay. Okay, we count. Okay, counter nums. This good. Frequency element. This is what I was doing. I don't know why this didn't work well. For each element, push the player count element. Yes. Smallest element, the one with the minimum frequency. Okay. Okay. And complexity. Mhm. No, this is shit. This is really shit. Frequency counter. Nah, this is shit. I want efficient approach. Mm-hmm. Yes, it's shit. This is what I'm facing. I'm not limiting the heat. Mm-hmm. What? I'm gonna rub this. I'm gonna rub this. This is really weird. So we just need okay. Okay. Let me erase this. I want to see this anymore. So if we look at this method, I think this method works good. It's like iterating elements and creating a hash map. So I'm gonna use that method. Run count count. What? Counter. From collections import counter. Okay. Yes. And frequency counter is called frequency counter. Yeah. I want to see what this little thing returned. Frequency counter. Some little intrigue. It's like an array. It's like a hash map. Yes, it's like a hash map. Heap, heap, h. Heap h. Yes. Let's see what the heap looks like. Print heap. This is interesting. 2231. 2231. Frequency and number. Yes. Frequency and number. Just need to return again how this shit works for x in something like this. return x for x in num for count num in h, I guess. I don't know if this is correct, but anyways, yes, to one expected output. It doesn't matter the order, so it should be fine. But the thing is, moment of truth. Let me see if 8 milliseconds. Holy shit, this is amazing. What the fuck? This is really amazing. So, what the fuck I'm doing here? What if I replace 8 milliseconds 20? Yes. Default dict. What? Default dict int amounts. List amounts. Really? So sorting, really? No, can't believe it. This. But well, what the fuck happened here? Well, let me explain. We create a counter. It's like creating a hash map with, I don't know if this is the same as we do this frequency counter. If we do this, it's like iterating this one. Oh wait, loud open or item in in nums. If I'm gonna use the key as num value, yes, num frequency, yes. If frequency counter well, is there a better way to do this? Count elements array Python hash map, something like this. Now without using this is the manual iteration. So it's on Pythonic approach. Hashable objects, yes. Counter my list, yes. This is what I want. It's the most it's the most what? It's the most concise approach. No. I don't know if this is the same as, I think so. It's even better. Holy shit. It's even better than using the counter method. Holy shit, this is amazing. This is really amazing. This is really amazing, bros. This is really amazing. Yes, 3 milliseconds. Holy shit, we moved from like more than a second to 3 milliseconds. It's unbelievable. I know that this is not a very hard problem, but hey, using heaps, it was good. But by the way, let me try to understand this. We don't need the counter, so this will be our final solution. We don't need any more. So what we're doing here, well, simply we count the nums using a simple count function. Then we initialize the heap, and it was what we saw in this documentation. It's like a tree, a complete tree, binary tree. No, it's like a complete binary tree, I guess, which is sorted from top to bottom, from root to leaf, but it's not sorted at, I don't know, leaf level, something like that. But here we are pushing to the heap, but we are using previous quick and num, yes. And internally the heap is sorting from min to max. And the array, yes, the array, yes, yes, yeah. I know why we get this result unordered. Yes, I know why. Because we are using a min heap. Min heap is increasing order, but we are maintaining the length of the heap of of a size of key. So if the heap, I don't know, overcomes the key, we remove the first element. So this element will be the less valued element. So when we remove this element, you know what? I'm gonna grab my tablet, explain in more detail this. So we are here. So if we have, for example, if you have this array of numbers, I'll show you why. Yes. Well, 1, 2, 3, 1, 3. Then we create the counter, right? So we create the counter. So the counter will be something like 1 is 3 times, no, 2 times. This is frequency, right? 2 is 1 time, and 3 is 2 times. Well, I'm gonna add under 3. 3 is 3 times, right? Then we iterate this or convert this to a heap, and the heap will be something like this. The key of the heap will be the frequency. So the first element, and at the first iteration, let me create iterations. So the first iteration, the item will be this, right? So the heap will be added with like this. This will be the first iteration, so it's gonna be 1, and the value, I don't know how to call this. Well, this is gonna be the key, right? So the first iteration will be something like this. At the second iteration, the heap will be something like this. 1, well, in fact, it's gonna be 1, then 2. Yes, regarding the key, right? Then, for example, we will assume a key of 2, by the way. Internally, when we use the heap push function, we add to the heap an element, but this element is sorted vertically, right? So in this line will be sorted. In this case, a min heap, meaning the root is less than the leaf. This is a min heap. So then at the third iteration, we will have something like this. 1, 2, 3. But we have the function to delete the last element of the array. That's the last element of the heap, sorry. So when we execute the heap pop, remember heap pop, we will remove the root, simply the root. So we will remove this. So this will be gone. So at the end, we will have the most frequent elements. And that's the magic of all of this. Having the most frequent elements, because the array will be coded, something like that, will be coded on each iteration to preserve the key size, or the size of key. Key, remember, is the size of the heap. So with this line of code, we are preserving that. And in that case, for doing that, we will have, at the end, we will have the most frequent elements, but unsorted. But reminding that this problem doesn't reject or allows any order on the answer, so we will be fine. I feel great because we could, with a little help, but we will in the right place. So that's something to value of this stream. We were doing the things good, following the docs of what is a heap and something, because I didn't know, or I didn't knew what was a heap until now. So it's good to know, with a little help, the solution and to improve them, because if you saw this in the solution, it was using counter, but we saved like 5 milliseconds using a regular counter. Yes, submissions. Look, we have 8 milliseconds, and here we have 3 milliseconds by just changing a couple of lines of code, and that is the magic of coding. So with more than an hour and 20 minutes, we finally finished our day number 4. So I feel great because I learned a couple of things about heaps and how can it be useful. So thank you guys if you stayed until here.